This is an audio recording for visually impaired students, Organic Chemistry, Chapter 2, Organometallic Compounds. Heading 2.1, Introduction. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc., form such compounds. The organic part is generally an alkyl, alkyl, or aryl group. They are named simply by adding the name of the metal to the name of the organic group linked to the metal. For example, methyl lithium, ethyl magnesium, N-butyl lithium, diethyl mercury, triethyl lead, phenyl lithium, dimethyl leadmium, diethyl zinc. The carbon metal bond in organometallic compounds differs widely, varying from bonds which are essentially ionic to those which are largely covalent. For example, largely ionic C negative and M positive. Thus, the extent of the ionic or polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence: carbon calcium the lowest, then carbon sodium, then carbon lithium, carbon magnesium, carbon aluminium, carbon zinc, carbon cadmium, and carbon mercury the highest. The reactivity of organometallic compounds also depends upon the nature of carbon metal bond. Generally, the larger the ionic character of carbon metal bond, more reactive is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of the reaction. Organometallic compounds are extremely useful for the synthesis of vast variety of organic compounds. Apart from these, many of organometallic compounds are commercially important as well. For example, tetraethylate is extensively employed as an anti-knock compound. Organotin compounds are used as antioxidant in rubber products. Phenylmercuric acetate is used as a fungicide and disinfectant, and organocenic compounds are used in medicines. Heading 2.2, Organomagnesium compounds or Grignard reagent. Organomagnesium halides are extremely important reagent in synthetic organic chemistry. The reagent are commonly known as Grignard reagent after the name of the discoverer Victor Grignard received the Nobel Prize in Chemistry in 1912 for this discovery. The general formula of Grignard reagent in RMGX or ARMGX, where R represent the alkyl group and AR represent any aryl group. Heading 2.2.1, Preparation. Grignard reagents are prepared in the laboratory by the action of an alkyl or an aryl halide on magnesium metal, turning in dry ether. Rx plus Mg in presence of dry ether gives out RMGX. Besides ether, tetrahydrofuran THF, dioxane, dimethoxyethane DME or dimethyl ether, glycol, tertiary amines, etc. can also be used as solvent. In fact, THF is considered to be the solvent since it increases the reactivity of an alkyl or aryl halide towards magnesium. It is because of the reason that the Grignard reagent of less reactive aryl and vinyl halides, which are difficult to prepare ether, are prepared in THF. Further, it has been found that for a given alkyl group, the ease of formation of Grignard reagent is in the order iodine the highest, then bromide and chloride the least. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen atom, the order of reactivity is CH3X the highest, then C2H5X, then C3H7X, and so on. That is, the formation of Grignard reagent becomes increasingly difficult with increase in the number of carbon atoms in the alkyl group. The use of tertiary alkyl iodide is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagent. Alkyl or aryl halide is added slowly to perfect clean and dry flask containing dry magnesium turnings covered by a layer of absolutely dry ether. The reaction mixture is warmed a little when exothermic reaction should soon start. If the reaction does not start within 5 minutes, a few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloudy solution of the Grignard reagent. Precaution in the preparation of Grignard reagent. During the preparation of Grignard reagent, the following precautions must be observed. First, the apparatus should be perfectly dry and protected from moisture by using a CaCl2 guard tube. Second, all the reagent and solvent, that is alkyl or aryl halide, magnesium metal and ether must be absolutely dry. Third, ether used as solvent must be completely free from alcohol. This can be done by first washing ether several times with water, followed by drying over anhydrous CaCl2 for 1 to 2 days and subsequent distillation over sodium. Fourth, an atmosphere of dry nitrogen, free from oxygen and carbon dioxide, should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture and react with oxygen and carbon dioxide to form alcohols and carboxylic acid respectively. The etherical solution of Grignard reagent thus obtained is generally used as such for various reactions by adding to it the other reagent. Mechanism. The mechanism of the formation of Grignard reagent is still not certain. According to Gomberg and Beckmann, 1930, the reaction commences with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism. Rx plus Mg plus Xr gives out R bond plus MgX2. These mechanisms also elegantly explain the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodide. Heading 2.2.2 Structure of Grignard reagent. The structure of Grignard reagent has not been finally settled so far. The recent research has shown that the actual structure varies with the particular Grignard reagent and the solvent used for its preparation. Grignard and Blaise 1901 observed the evaporation of etherical solution of Grignard reagent resulted in a white solid having the composition RMgX.2C2H5 twice O. This suggested that ether molecules were present as ether or of crystallization. X-ray analysis of these dietherates suggest that the four groups are arranged tetrahedrically as shown in formula. Thus, formula suggests that ether does not merely provide a medium for the reaction, but it also helps to dissolve the Grignard reagent formed due to solvation by ether molecules. This is supported by the observation that Grignard reagent can be prepared even in benzene solution in presence of a tertiary amine, which coordinate with magnesium like ether and thus dissolves it. Further formula shows that Grignard reagent in the monomeric form, but physical studies have revealed that Grignard reagent exists as 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with molecules of ether. These two species are held together by halogen bridges as shown in formula. R2Mg.MgX2 gives out R2Mg plus MgX2, which further gives 2MgX, that is Grignard reagent. However, for the sake of convenience, the formula RMgX has been used to represent alkyl magnesium halide in the text. Heading 2.2.3 Reactions of Grignard reagent. The carbon-magnesium bond in Grignard reagent is highly polar due to large electronegativity difference between carbon and magnesium, 2.5 to 1.2, that is 1.3. Consequently, due to greater electron density around carbon, the alkyl group in Grignard reagent act as carbon anion or a nucleophile, that is, it can attack any electron deficient center in other molecules. Other words, Grignard reagent chiefly undergo nucleophilic substitution or nucleophilic addition reaction. First, nucleophilic substitution reaction. Grignard reagent react with compound containing an acidic hydrogen or halogen atom. All such reactions involve the nucleophilic attack of alkyl group on Grignard reagent on the electron deficient center as shown below. Second, nucleophilic addition reaction. Grignard reagent react with compounds having a multiple bond such as C double bond O, C double bond S, C triple bond N, etc. to form addition product which when hydrolyzed yield a variety of compounds. In all such reaction, the addition of the nucleophilic group of RMgX, that is R, occurs at the more electropositive end and that of MgX group at the more electronegative atom of the multiple bond. Thus, C double bond O plus RMgX gives out CROMgX in presence of H2O and H positive, which gives out an alcohol plus MgOHX. Heading 2.2.4 Synthetic uses of Grignard reagents. Grignard reagents serve as extremely valuable starting materials for the synthesis of a vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other class of compounds. To illustrate this, some important synthetic applications of Grignard reagent are described below. First, alkenes. A. By action with active hydrogen containing compounds. Active hydrogen containing compounds such as water, alcohols, thioalcohols, carboxylic acid, hydrogen sulfide, ammonia, amines, terminal alkynes, etc. react with Grignard reagent to form and corresponding to the alkyl or the aryl group of the Grignard reagent. RMgX plus HB gives out RH plus MgBX, where B is OH, OR, SR, OCOR, NH2, NHR, NR2, etc. Since methane is evolved quantitatively when CH3MgI is treated with compounds containing active hydrogens, therefore these reactions can be used for estimation of OH, NH2, SH groups in organic compounds. The method employed is called Zervetinon method. Aryl magnesium halides also behave in similar manner. Example, phenyl magnesium bromide plus HOH gives out benzene plus MgOHBr. B. By action with reactive alkyl halides. Grignard reagent react with reactive alkyl halide such as tert butyl chloride, benzyl chloride, etc. to form alkenes. Second, alkenes. Grignard reagent being weak nucleophile do not react with simple alkyl halide. However, compounds containing more reactive halogens such as allyl iodide, etc. react with them, giving alkenes. Third, alkynes. Grignard reagent react with terminal alkynes forming alkyl Grignard reagent upon treatment with alkyl halide give higher alkynes. Fourth, primary alcohols. A. By action with ethylene oxide followed by hydrolysis. Grignard reagent with ethylene oxide to form addition product which on hydrolysis with dilute hydrochloric acid form primary alcohols containing 2 carbon atoms more than the alkyl halide. B. By action with formaldehyde followed by acid hydrolysis. When treated with formaldehyde, Grignard reagent forms an adduct which on hydrolysis with dilute hydrochloric acid gives a primary alcohol. C. By action with oxygen. Primary alcohols are formed by passing dry oxygen through the solution of Grignard reagent followed by acid hydrolysis of the resulting addition product. Fifth, secondary alcohols. A. By action with aldehyde other than formaldehyde followed by acid hydrolysis. B. By treating an excess of Grignard reagent with ethyl formate, the reaction takes place in 2 steps. Grignard reagent first react with ethyl formate to form an aldehyde which in turn react with another molecule of Grignard reagent to yield an adduct which forms a secondary alcohol on hydrolysis. Sixth, tertiary alcohols. First, by action with ketones followed by hydrolysis. Second, a tertiary alcohol having at least 2 similar alkyl groups may be prepared by the interactive between an ester other than formic ester and an excess of Grignard reagent. The reaction proceeds in 2 steps. Third, by reaction with acid chloride and anhydrides. Grignard reagent react with acid chloride or anhydrides to give addition product which upon acid hydrolysis give tertiary alcohols. The reaction takes place in two stages. 7th, ethers. Grignard reagent react with lower halogenated ethers to yield higher ethers. 8th, aldehydes. A. When a Grignard reagent is treated with ethyl formate, an aldehyde is formed. However, with excess of Grignard reagent, the product obtained is a secondary alcohol. B. Aldehydes are obtained in a better yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in the case prevents the formation of secondary alcohol. C. Aldehydes may also be obtained by the interaction between a Grignard reagent and hydrogen cyanide followed by hydrolysis of the adduct formed. 9th, ketones. A. By treatment with alkyl cyanides followed by acid hydrolysis. B. By action with acid chlorides. As discussed on page 83, equimolar amount of a Grignard reagent and an acid chloride give an addition product which forms ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as ultimate product of the reaction. 10th, monocarboxylic acid. Grignard reagent interact with dry ice, that is solid carbon dioxide, to form acid addition product which on acid hydrolysis give monocarboxylic acid. 11th, esters. By action with ethyl chloroformate. Equimolar amount of a Grignard reagent and ethyl chloroformate react together to form higher esters. 12th, thioalcohols. Grignard reagent react with sulfur to give an addition product which gives a thioalcohol on hydrolysis. 13th, phenols. Aryl magnesium halide react with oxygen to form addition product which upon hydrolysis give phenol. 14th, alkyl cyanide. By interaction of Grignard reagent and cyanogen chloride or cyanogen, excess of Grignard reagent is avoided since it will react further with alkyl cyanide to yield ketone. 15. Primary amines. Grignard reagent react with chloramine to form primary amines. Reasonable yield of primary amines is obtained only with Grignard reagent containing tert alkyl groups. Primary amines can also be prepared in satisfactory yield by the action of Grignard reagent, chloride or bromide but not iodide, on orthomethyl hydroxyamine. 16. Sulfenic acid. On passing sulfur dioxide into a well-cooled solution of Grignard reagent, an addition product is obtained which on hydrolysis gives sulfenic acid. 17th, dithioic acid. These are prepared by the action of Grignard reagent with the carbon disulfide followed by acid hydrolysis. 16. Organometallic compounds. Grignard reagent and inorganic halides interact with each other resulting in the formation of other organometallic compounds. Heading 2.2.5. Abnormal addition of Grignard reagent. First, addition to hindered ketones. If the Grignard reagent or the ketone contains branching at the alpha carbon, sometimes the usual addition reaction does not occur due to steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagent to the ketone via a 6-membered cyclic transition state in a manner similar to Merivin-Pondorf-Verley MPF reduction. For example, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected 3-degree alcohol, that is isopropyl carbonyl, is not formed. Instead, the secondary alcohol, diisopropyl carbinol, is obtained by reduction of the keto group. Second, addition to alpha beta unsaturated compounds. Alpha beta unsaturated carbonyl compounds react with Grignard reagent to give 1,2 and 1,4 addition products. The orientation of addition is often controlled by steric factors. In general, substitution at the carbonyl group favors 1,4 addition, while substitution at the double bond favors 1,2 addition. In most cases, both products are formed, but alpha-beta unsaturated aldehydes nearly always give exclusively 1,2 addition product when treated with Grignard reagent. However, the extent of 1,4 addition of Grignard reagent can be increased by carrying out the reaction in presence of cuprous chloride or cupric acetate. This is called conjugation addition and probably occurs by a free radical mechanism. Heading 2.2.6 Limitations of Grignard synthesis. Grignard reagents suffer from the following limitations. First, Grignard reagents are sensitive to moisture, oxygen, and carbon dioxide and hence must be protected from them. This makes the handling of Grignard reagent difficult. Second, Grignard reagent cannot be prepared from alkyl halides containing other reactive functional groups such as OH, SH, NH2, C double bond COOH, SO2, CHO, C double bond O, COOR, CN, etc. Since they all react with them, only alkyl halide containing a few other groups such as R, OR, AR, X, etc. can be used to form Grignard reagent. Third, generally branching of the carbon chain near the functional group prevent reaction probably due to steric hindrance. For example, CH3-MgBr or CH3-MgI does not react with di-tert-butyl ketone, that is CH3 whole thrice C bond CO bond C CH3 whole thrice. Similarly, if the Grignard reagent contains large alkyl group, the reaction is sometimes prevented again due to steric hindrance. For example, isopropyl methyl ketones react with CH3-MgI but not with tert-butyl magnesium chloride. Fourth, compounds which are capable of enolization liberate hydrogen with Grignard reagent. Fifth, nitro compounds cannot be used in Grignard synthesis since they oxidize the Grignard reagent. Despite the above limitation, Grignard reagents are still the most important tools in organic synthesis. Heading 2.3 Organometallic compounds. Although organometallic compounds of the type R2ZN are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. Heading 2.3.1 Methods of formation. Following methods have been used for the preparation of organometallic compounds. First, from alkyl halide. Alkyl iodide react with zinc copper couple in high boiling ether to form alkyl zinc iodide, which upon subsequent distillation in an atmosphere of CO2 undergo disproportionation to give di-alkyl zinc compound. Second, from organoaluminium compound. Treatment of trialkyl aluminium with zinc chloride give dialkyl zinc compound. This method forms the basic of laboratory preparation of these compounds. Heading 2.3.2 Physical properties. Dialkyl zinc compounds have linear geometry due to sp hybridization of zinc atom. They are non-polar, low boiling liquid or low melting solids soluble in organic solvent. The lower zinc compounds are highly inflammable in air and hence are usually prepared and used under CO2 atmosphere. Heading 2.3.3 Chemical reaction. The chemical reaction of organometallic compounds are similar to those of Grignard reagent, with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanides, ketones and esters. Some important chemical reaction of dialkyl zinc compound are discussed below. First, reaction with water. They readily react with water, forming alkanes. Second, reaction with alkyl halide. Dialkyl zinc compounds do not react with 1 degree and 2 degree alkyl halides. They react only with 3 degree alkyl halide to form alkanes containing a quaternary carbon atom. Third, reaction with acid chloride. They react readily with acid chloride to form ketones. Ketones are obtained in good yields because dialkyl zinc compound react very slowly with them. Fourth, Reinforcement-Sky reaction. When an aldehyde or a ketone is added to the solution of an alpha haloester in presence of zinc, an organometallic compound is first formed, when then adds to the carbonyl group in a manner similar to the Grignard reagent to form a beta hydroxy ester. This reaction is called Reinforcement-Sky reaction and is usually a useful method for preparing beta hydroxy esters and their derivatives. Heading 2.3.4 Isomethyl zinc iodide. Idomethylene zinc iodide is an important organometallic compound and is obtained by the action of zinc copper couple on methylene iodide. If it reacts with olefins to form cyclopropane derivatives. This reaction is called Simon-Smith reaction and is used for preparation of cyclopropane derivatives. The addition occurs in a stereospecific scene manner according to the following concerted mechanism. Heading 2.4 Organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are called organolithium compound. For example, CH3Li, methyl lithium, ethyl lithium, and butyl lithium, and phenyl lithium. Organolithium compounds are more reactive than Grignard reagent and also undergo a few useful reactions. Therefore, they are widely used in organic synthesis these days. Heading 2.4.1 Formation of alkyl lithiums. First, by reaction of an alkyl halide with lithium. Alkyl lithiums are generally prepared by treating an alkyl halide with lithium in hexane, benzene, or any other hydrocarbon solvent at a lower temperature in an inert atmosphere of nitrogen or argon. For the preparation of alkyl lithiums, hydrocarbon solvents are prepared ever ether, since the use of ether not only encourages Wood's reaction but also react with it. Second, by metal-metal exchange. Alkyl lithiums can be readily prepared by the replacement of one metal by another. Heading 2.4.2 Chemical reaction or alkyl lithiums. The carbon-lithium bond is more polar. Electronegativity difference 2.5 minus 0.9, which is 1.6. Then carbon-magnesium bond, electronegativity difference 2.5 minus 1.2, which is 1.3. Therefore, alkyl lithium are more reactive than the Grignard reagent. Except a few differences, their chemical behavior is similar to that of Grignard reagent. Some of their important chemical reactions are discussed below. First, resemblance with Grignard reagent. They resemble Grignard reagent in most of their reactions. Some of these reactions are formation of hydrocarbon. Like Grignard reagent, they react with compounds containing active hydrogen to form the corresponding hydrocarbons. Formation of primary, secondary, and tertiary alcohols. A. Primary alcohols by action with formaldehyde. Like Grignard reagent, alkyl lithium compound also react with ethylene oxide to form primary alcohols containing 2 carbon atoms more than the starting alkyl aryl halide. B. Secondary alcohols by action with aldehyde other than formaldehyde. C. Tertiary alcohol by action with ketones. Third, formation of ethers by action with monochloroether. Fourth, formation of aldehyde by action with ethyl orthoformate or hydrogen cyanide. Fifth, formation of ketones by action with any orthoester other than orthoformic ester or alkyl cyanide. Sixth, formation of nitriles by action with cyanogen chloride. Reaction with alkyl halides. Alkyl lithium react with aryl halide to form alkanes. Seventh, reaction with aryl halide. Aryl halide undergo nucleophilic substitution reaction by elimination, addition, or benzene mechanism. Eighth, reaction with heterocyclic compounds. Heterocyclic compounds undergo nucleophilic substitution reaction by bimolecular displacement mechanism. Difference from Grignard reagent. Organolithium compounds, being more reactive than Grignard reagent, undergo some additional reaction as discussed below. First, action with carbon dioxide. Grignard reagent yield carboxylic acid with carbon dioxide, while organolithium compound yield ketones. This difference is due to reason that organolithium compound are more strongly nucleophilic than Grignard reagent and thus react further with intermediate resonance stabilized carboxylate anion gives ketone. Second, action with carboxylic acid. Alkyl lithium compounds react with carboxylic acid yielding ketones as the main product. Grignard reagent on the other hand give alkanes corresponding to the alkyl group of the Grignard reagent. Third, addition to carbon-carbon double bond. Unlike Grignard reagent, organolithium compound add to simple alkenes to give a mixture of compounds. The addition occurs at high pressure. For example, RLi plus CH2CH2 in presence of hexane gives out RCH2CH2Li, which further gives RCH2CH2CH2CH2Li, etc. Fourth, formation of tertiary alcohols. Organolithium compounds, being more nucleophilic and smaller in size than the corresponding Grignard reagent, add to sterically hindered ketones to form sterically hindered tertiary alcohols. Grignard reagent, on the other hand, do not give addition reaction. For example, isopropyl lithium adds to diisopropyl ketone to yield triisopropyl carbinol. In contrast, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohols is not formed. Instead, reduction of the ketone by the Grignard reagent occurs due to diisopropyl carbinol and propylene. Fifth, reaction with alpha beta predominantly undergo 1 to addition to alpha beta unsaturated carbonyl compound, whereas Grignard reagent give mainly 1,4 addition products. Thank you.